Hi, good morning everyone. I'm audible. We shall be starting in a couple of minutes. So I think I can start the session now. So very good morning to everyone. Thanks for joining again in this session. Today, we shall be focusing on the FE modeling in some of the simple way, accompanied by material representation and how the tool can be used in the following field. So I'm just sharing my screen. So if any available, just confirm whether my screen is visible. Yeah. So, uh, as discussed, we shall be discussing about the 3D image processing for material modeling and additive manufacturing part. So, the following session is divided into two parts. So, In this morning session, we shall be covering out about the theoretical aspects. We shall be discussing about the features that we ought to be using in the afternoon session. In the afternoon session, since we weren't able to cover the finite element modeling part yesterday, so I shall be telling you how to operate the tool to develop any finite element models. Apart from that, how to do the particular material reverse engineering, that too will be covered. And last but not the least is the 3D printing part, how we can optimize any 3D printing approach in simple way. So without wasting much time, let me just continue with the presentation. So let us have a quick recap about what is simpleware and what are its capabilities. So as we have discussed in the earlier sessions, that it is a image-based modeling tool. And coming on to a materials engineering perspective, there's a need to understand why such an approach is very beneficial for us when we are working with very complex data set that is not very easily distinguishable. So why we are using this approach is because adoption of this 3D imaging technology will enable us to see both the external features as well as the internal features, and it can be used for both industrial as well as medical aspects. Apart from that, it has a wide range of finite element analysis and computational fluid dynamics code. So it has a great compatibility with the other softwares that are present like COMSOL, ANSYS, Abacus, BTK, MATLAB. And furthermore, it allows us to understand the true topology of the surface, what are the different materials, so multi-phase material if present in a single material that we can identify out. So the study of composite material becomes very easy for us. Now, coming on to the next part, how this simpleware is again offering. So as discussed, we can easily convert any 2D stack of images into 3D presentable model. We can use it for visualization. Then we can do the analysis of whatever data that we are working on. And last, if we are having multi-part models, for example, over this side, let me zoom in, or let me have a pointer. Yeah. So for example, if we are having this particular part and we can see the spinal region is a different meshing, then the cranial cavity has a different meshing, the skin has a different type of meshing, all the soft tissues are having different types of meshing. So this is basically a multi-part model where we can define each and every component as a separate component, set out its modulus and Poisson's ratio, and do the modeling accordingly. It can be used on any image stacks, being JPG, PNG, TIFF, and we have the multi-part structure support also. Apart from that, if we need to just visualize, if we need to just see whether to see any surface defect if present, if we need to just see the internal defect if present, we can just carry out the data set in the 3D view and then we can check for the following. Apart from it, if we need, once we have done the scanning, the modeling, we need to send those 3D printable files. So high quality watertight SQL files can be prepared and later on it can be shared with us for doing the 3D printing part. So all the particular workflow becomes very easy when we are dealing with simple web. Now, coming on to the again the application areas. So since in the yesterday and day before yesterday's session, we have discussed about the biomedical and biomechanics. And tomorrow's session also we shall be discussing about the cardiovascular and any vascular or soft tissue segmentation, the modeling of such tissues and the measurement. In this session, we shall be focusing on this part too, biomechanics part, but we shall be also seeing how we are using the software for materials, components, and geotechnical analysis. So, coming back to this material image processing. As explained, the software can be used for doing non-destructive analysis, non-destructive testing on any object. We need not to break the object in half to see the internal structure. We can just have a 3D scan model of the same, input the particular resultant files in simpleware, do the processing, set out the material properties, and ultimately do the simulation in any simulation-based software. Apart from that, any crack propagation, if we need to check, if we need to do the fiber analysis of any fiber-based composite material, that too can be carried out. Porosity analysis can be directly carried out. And last but not the least is the particle analysis. So if we are having multi-particle structure, we can do individual particle analysis of the same. We can check how the particular grayscale value is ranging from part wise to part wise. Then if we need to check on the mass density, that can also be done. Now, coming back to the other points that are covered is the reverse engineering part. So, if we are having any CAD object that we have designed in SolidWorks or any other uh, modeling tool, modeling software, what we can do is we can do the reverse engineering. We can scan the data set, put as input in simpleware, and later on use the surface deviation feature to check for the accuracy of the printed model versus the design part. So ultimately, we can increase the efficiency that is present for doing any sort of CAD modeling. And last but not the least is the natural sciences part in which the software can also be used for archaeology purpose. So we need not to break any part, or if the same technique, the 3D image processing technique was recently used to carry out and see inside literature books. So old literature books where the letter weren't very visible, what sort of literature was written in was not very visible. So what was done in that particular study was they had taken the book, they had done the 3D scanning of the same. If they have opened the book, then the particular pages might got have distorted, and it might destruct the particular nature of literature that was present. So what they had done is they had done the 3D scanning of the same, and later on input in the 3D reverse engineering software, and later on they were able to see what is written inside the book even without opening it. So this is one such feature for which the particular reverse engineering part can be used for archaeology. Same can be done with paleontology. So uh, the fossils that are present to do fossil analysis, how was the shape to determine the particular shape of the actual fossils that were present. So prehistoric creatures, we can do that easily using such technology. Now, coming back to the basic workflow that we have done. So the workflow is pretty same when we are coming on to the material reverse engineering as compared to the biomechanical modeling. So what we generally do is we do the first acquisition of the data set. Once the acquisition of the data set is conducted, we can import the data set into CT, MRI, micro CT, and for industrial images, since we are focusing on, so we can also import the file in the form of dicot. Once that is done, we move on to the processing part where there are several steps involved. The first one being the pre-processing to reduce out the region of interest. This is very much useful when we are dealing with material part as they have the data set in memories around 10 GB, 20 GB, and even 50 GBs of data. And to process such huge data is a quite tough task because the hardwares are not that capable to deal with such a set of data sets. So what we can do is, for example, if we need to do a part-wise inspection, so we can just reduce down the region of interest to the specific part and later on carry out the modeling. And over here, this is one such example of a composite material that was used in which different parts were identified and then the properties were later on assigned specific to the particular composite part. So it was a composite aluminum material for which the reverse engineering was done. Now, coming on to the segmentation part, in the segmentation we can segment out different regions that are present. If there is any sort of artifacts or defects that are present, what we can do is we can just go over there, and here we can carry out and see if the particular feature is a part of the material or it is due to any metal artifact or any other defect that is present. So this way we can do easy detection. Then comes the particular analysis and result part. Once it is done, we generate out the report, and the reports can further be used to do any sort of simulation that is required. And ultimately, all the main aim of our work purpose is to do the diagnosis, to carry out the result, to correct the particular structure that we are working on, and later on the visualization and reporting task can be done. Moving on to the next part is again the different features that we cover. So that is the segmentation and processing part. Then we have the measurement and analysis that can be done, model generation, finite element model, computational fluid dynamics model, non-uniform rational B-spline structure model, Then the 3D image important visualization. For example, if we need to just see how the volume rendering is performing, that can be checked from here. Integration of CAD and image. So since we are working on city data or any other JPG stack of images, KIFF stack of images, and we need to integrate with any CAD file. That can be done in an easy way. And later, last part is the API generation, which was discussed at the end of day one, how we can do the automated scripting, how we can generate scripts for any part. And once the particular scripting has been conducted, we have generated the script, how it can be used in the other workflows that have similar set of data. So coming back to this image import and visualization, so the first step being whenever we import a particular image, we can see over here the particular sample that was taken is an auxetic form sample that has a negative coefficient value, and this particular sample is present in the database library that we can further check. So what was done? The data set was imported and we get the respective views, the XY view, the XZ view, and the YZ view. And corresponding to these three views, we have generated a volume render. You may observe that it is not that clear and we can't basically see the structure in a proper way. So what was done to see the particular structure was we have used various volume rendering settings to interchange the files to reduce out the vacuum region that was present. And once that was done, we can have a better and clear visualization of the same. Also, in this case, a co-registration of the image data set was done to have a much more accurate representation and much more accurate finite element modeling to be conducted for. Now, coming on to the visualization. Visualization generally depends on our GPU capabilities. If we are having a high-end GPU, if we are operating on a high-end GPU, the task becomes very easy for us and we can easily load multiple structures in a quick span of time. But if we are just dealing with a CPU-based data set, it might take time. Apart from time, it might also consume other resources and it may slow down the system. So it's generally recommended to use and operate simpleware software on a GPU-enabled system. Then the session where we shall be focusing on the particular part in which the segmentation is performed using multi-level output and how the output varies when we increase the number of masks in multi-level auto segmentation. Then the other feature being the region growing, in which if we are required to find out small features that are being present in the data set, so we can use our operations such as a region growing operation. Then we also have flood fill operations to remove out any disconnected regions if required. We can also use split or merge operations since our software is based on watershed algorithm. So any important segmentation that required can be done in a very easy way. We also have a slice to slice propagation way, so we can reslice the images along any point. So for example, along this edge to this edge, if we need to do the reslicing or we need to do the multiplanar reconstruction, that can be carried out in a single click operation. And the last one, but not the least one, if we are using a magnetic resonance imaging of any data set. So we can also do the counter based magnetic lasso correction. And even if there are small deformities present, it can be sorted out in a very efficient way. Now, moving on to the measurement and analysis. This is one such important aspect that when we are dealing with any material. So the first one being to do the fiber analysis. So fiber analysis is a complete tool in simple way. We need not to rely on FE module for that. We can just, whenever we are having a fiber data, one such data is present in our example dataset library, wherein we can set out the particular fibers. Once the particular fibers are set out, what we need to do is we need to check the orientation. So corresponding to each and every fiber that is present, we can map out the orientation of that fiber, and we can also check the angle corresponding to the principal axis that is taken. So whenever we are taking all the particular principal axis, we can just check out the angle deviation of each and every fiber that is present in the material. Apart from that, we have multiple analysis and multiple plot generation capabilities that we can further use to identify the different region. Also, if we are working on any grayscale based data and we need to identify different properties corresponding to the grayscale based data, that too can be done. Once we have identified the different segmented region, we can move on to the analysis part. And in the analysis part, we can easily identify the different parts and later on generate the plots. For example, the volume versus the frequency of the data set, how frequent is data set, which material is how frequent. We can just check corresponding to volume graph. So these are some of the easier measurement capabilities. Then we also have the automatic wall thickness assessment, where we can use two types of algorithm. Either we can use a raycasting algorithm or a general algorithm, wherein we can check for the wall thickness accordingly. Also, we have another approach whenever we are dealing with certain complex data set in which the boundary is not very easily distinguishable between two different materials present in a composite material. So what we do for such cases is we identify the particular boundaries, the region of boundaries, and then a particular higher meshing is done for the specific data set, and later on the calculation is done. Also, for such cases, we generally recommend to use a profile line tool to have a clear identification of the grayscale variation. Apart from it, if we need to just check out any fractures in the dataset if present, we can do in a single click operation in the form of check and fix in the surface tools option. So there are multiple options that we can do. Then coming on to the CAD versus the scan part. So for example, this is a gear design that we have designed in a STL format in SolidWorks software. So what we did was the particular part was again scanned, and then since this being an STL file, surface file, and this once the scanning is done, we have done the segmentation. We have obtained a surface file from the same. So this was overlapped, and we could see what change of result is being generated once we are doing overlapping. So we can check for the breakpoints present in the data set, what's the lower deviation value that can be checked, what's the upper deviation value that can be checked. So we can have a proper graph corresponding to that what's the minimum deviation corresponding to which point and what's the maximum deviation. And the green region that you can see is the complete overlapping of the cat part with the scan part that we have done. Apart from it, yeah, since we are dealing with 3D printing also, so What we have is we have the option of setting the internal latex structure to reduce the weight of any CAD or any image data if present. Later on is the model generation part that I'll further cover in the upcoming slides, where we will discuss how the different types of models are generated. Before that, let us see what are the export capabilities just for the model part. So for a surface model, we have the following export capabilities. So we can export in STL, IGS, ACES, ANSYS Surface, Open Inventor, Point Cloud, and multiple export formats. So multiple softwares are supported. For finite element modeling, also we have a detailed export option. Also, the additional feature that we get in the finite element modeling and simpleware is we need not to do the remeshing again in the analysis software. We can do the same and carry out the same in simpleware itself. Later on comes the CFD modeling part, wherein we can mark the particular uh, we can export the particular file in Fluent, Abacus, OpenFOAM, and COMSOL. Generally, OpenFOAM and COMSOL are used, but we also have other options like using Fluent for having a proper flow analysis in a blood pool model or in a heart model or in a cardiovascular other data set. So, since this was the part that was discussed, where we had shown the particular scripting part, how to generate the script, how to automate the script, so these are the different options that we generally have while we are working. So this was also shown in the live demonstration. Uh, on the day one, here we can select a particular part, we can convert into a Python file or a C# file. Once the particular conversion is done, we can save the Python file or C# file, and later on the API script can be run in our software. Now, coming on to the next part is the volume mesh generation. So this is one such important aspect in the tool that is the least discussed but has very high importance. Why so? Because whenever we are dealing with any image data set, whenever if we need to export it the particular image data set into any CAD software or any analysis software directly, it won't take place because the particular software doesn't recognize the image process data. For example, they can't work on a DICOM data set, or even if they can not work directly on the scan IP project file database. So what we have for that is we have a complete option. If we need not to rely and we are much more dependent on the FA modeling in any simulation software, what we can do is we can just generate a surface mesh for the same. So we will be having a proper structure. We will be having a smooth structure without loss of any topology. We can have the volume preservation. If multiple parts need to be added, that can be done in the Boolean operation. But whenever we are exporting the particular file, we can export the file in the any format that is required and do the remeshing over there. So if we need to set out the boundary condition, the contact points, node points, shells, if we require to do the mesh refinement, that can be later on carried out in the simulation-based software. Now, there is one more need to understand how the software plays a crucial role in doing the volume preservation. So when we are working with volume preservation, a general example of a femur was taken in which the image processing was done and the particular unsmoothed voxel count of the particular femur came out to be around 204 millimeter cube. And since whenever we are obtaining such a femur data set to do the analysis or even to do the particular 3D printing, we require a smooth surface because such type of surfaces, such type of rough surface might cause problem or might also distort our printing process. So we are required to do the smoothing. But a traditional smoothing operations that are generally present are the Gaussian filters, the mean filters that smooth out a little too much of the surface, and we have lots of features in that case. For example, you can see and focus on this specific part that the curvature has been decreased by a significant margin. So because of this curvature decrease when the smoothing was done and again the volume was calculated, so it came out to be around 194 millimeter cube. That is around 10.1 millimeter cube less than what used to be in the unsmoothed voxel model. So we have lost a lot of feature. It's around 5% loss, which is a significant loss. And when we will be simulating the particular
finite element model, or even if we are doing for a general purpose for 3D printing, we have lost lot of features in that particular case. And if we are dealing with patient specific data set, it may cause a huge problem, because the when we will be developing any implant corresponding to this data, the results won't be that proper. So what we have in simpleware is a smart match smoothing operation that works on a proprietary principle to do the smoothing on the basis of the grayscale value. It repeats over the process. It repeats. It has a number of iterations. It repeats the process again and again to smooth out the surface. And this way, the particular volume preservation can be taken into mind and into consideration. And we lost minimal of features in the following case. How so? Because we have two sets of approach. Either we can use a recursive quotient, where a value between 1 to 2 is recommended for a greater and smoother structure without loss of any features, or we can use a smart mass smoothing, and the result came out to be very impressive. It came out to be around 203.5 millimeters cube, which is quite efficient, because the unsmoothed voxel count was around 204 cube, and it's just less than 0.5% of loss. So this is a very great improvement that we are dealing with when we are using simpleware software. Now comes the uh, smart part in simpleware. So we have the automatic handling of various multi-parts that are present in our segmentation software. So whenever we are identifying multiple parts, the main issue that arises is how to identify the boundaries, and what if the particular boundaries are not properly mentioned, and we might have the loss of features, which will ultimately result in the loss of simulated values. And whenever we are doing research, we need to take the accuracy as the topmost priority. So that can be done in a very easy and efficient way. We can use a histogram peak to identify the different materials that are being present. And once we have used the particular histogram peaks to identify the material, the parts have been distinguished, the parts have been identified into different regions. What we can do is we can move on to our next part, is to do the particular meshing. And it is the tricky part, because when we are using a traditional approach where we have built the parts one by one, you can see whenever we are dealing in the boundary condition, it has lost some features over here. So it's around 10 triangles lost in total over a smaller section, which is a huge amount. Similarly, over this particular boundary condition, whenever there is a curvature, there is a loss of feature. So we have two sets of approaches to convert these data into accurate FE models. What we can do is either we can use a FE model tab to accurately define the boundaries and increase the particular mesh size and mesh fineness over those particular points, also accompanied by the contact pairs and the node sets that we need to use. When we increase such value, it will ultimately result in high value output, and further the accuracy is quite good. Now coming on to the finite element modeling. We have covered a slight part in the yesterday's session, the live demonstration one, where we have discussed how to develop a FEA model directly, but we weren't able to completely cover of the topic. So again, coming back to the particular finite element module tab. So the simpleware, in the simpleware software, the finite element module is not just accompanied by the finite element modeling, it is also accompanied by the computational fluid dynamics modeling. The CFD modeling one will be covered out in tomorrow's session, when we will be covering out the vascular structures, because the particular CFD analysis is generally used for fluid analysis, and for vascular structure it might be used, or for example for a heat sink if we are doing any fluid flow analysis, in that cases it can be used. But coming back to the particular finite element modeling part, so we are given the two sets of algorithm, the finite element free method and the finite element grid method, that I'll be covering out in the next slide, how each of the method is selected, which is the best choice of algorithm depending on our part by part, how we can use the user defined refinements to refine the particular meshes that are being present, how to add the contact points, the node points, and the shells that are required. So this way we can cover out each and every aspect. Here, one more option that we get is we can have the mix of tetrahedral and hexahedral elements within our finite element mesh. We can have curved quadratic tetrahedral elements. We can have the linear quadratic tetrahedral elements, and we can also have the straight edges. So we are given with the multiple options when we are dealing with the elemental type. Apart from it, one more important feature is the grayscale specification. So we can assign the material properties just on the basis of grayscale, and it further reduces the uh, inaccuracy while we are generating any FAA model. Because once we are defining the grayscale range, we identify the different phases that are present in material in a very efficient way. And once that is done, the part becomes very easy for us. Since I was discussing about the finite element tree part, so here is how the particular algorithm works. Whenever we are doing a particular finite element modeling, since it is a multi-part mesh structure, so we can set out the coarseness and the fineness individually. For example, for the outer part, we have taken a fineness of around 0, and for the red region, we have taken a fineness of around 25. So we will be having the increased number of elements over here. We will be having a increased number of nodes over here, and the aspect ratio will come out to be around 1.5 to 5.8. But when we are just decreasing the value to around 50 minus 50, we can see we have a coarser mesh around here. The triangles are quite bigger. And how the particular principle works is, I think many of you are familiar with finite element modeling, but just to give a brief overview how it works in biomedical case or any case. For example, we are taking a triangulated part. So let me take one pen. Yeah. So for example, if we are having a triangulated part over here, and we have told that this is one such element that we have taken, which has the coarseness level corresponding to minus 50. And we are again taking one more triangle. So it's the same dimension, the outer dimensions are same. But we have further divided this triangle into multiple small triangles. So we have done this, we have done this, this, this. Now, what we are doing by this particular method is, earlier the coarseness was taken as minus 50. Corresponding to it, the particular, when we have done the meshing, so a large part of this particular skull region that was taken was covered in a single triangle. Now, when we have increased the particular coarseness, of we have increased the fineness over here, so it's somewhere around minus 30 or minus 25, we can say. We have increased the number of triangles in the same specific set of area. And once we have increased the number of triangles, so we can assign different property for this triangle, we can assign a different property for this triangle, we can assign a different property for this triangle. And similarly, the smaller the number of elements, the higher the accurate the model would be, and the higher would be the efficiency for our calculation. So when we have increased this particular when we have decreased the particular coarseness, so we can see the aspect ratio becomes 1.7 to 4.8, and the element count also decreased from 973,000 to just 30,000, and the node sets also get decreased from 190K to just 7K. We can see how the particular uh, option varies the triangulation around the boundary condition. So this way, the algorithm that we are using, we can depend on it completely in a simple way. Now coming on to the non-uniform relational B-spline structure modeling. What we have in nerves modeling is we can develop high accurate nerves model. So whenever we are developing such model, you can see earlier we were depend on the triangulation, we were depend on the triangulated surface to model out our set. Now what we are relied on, uh, so it's a polygon shaped structure. So we have created different sets of polygons corresponding to this particular surface. So whenever we are converting a 2D data set into 3D model, and it has a high level of curvature, so the parts can be easily identified out using nose patch fitting, and it carries an automatic set of algorithm to do the same. Here we can set the smoothing also of the particular surface, and later on we are given the two sets of export mechanisms. Either we can export as initial graphic specification file or a step file, whichever is required for our set of work. Next up is the CAD model. whenever we are taking, we can also take an examples of any insect, we can choose the particular image based modeling, and later on how the part variation, how the stress and strain is around the legs region. So these are some of the application that comes under the biomechanics part and the FNCFD calculation. Now coming on to the some case studies, so I have taken four case studies as an example. So two are from the industrial perspective and two are from the medical perspective, that is biomechanics and the CFD analysis that we can perform in using simple way. So in the case study one, we have done the non-destructive inspection of additively manufactured parts using the CT data. So what it was done, a particular industrial data set was taken. This is a 3D printed part that was taken to check for its accuracy. What we had done, we had used a Nikon scanner to just scan out the part. Then it was also used a heater to just have a high accurate model of the same to be generated. Once this is, particular model was done, the main purpose of this study was to check the as designed part versus as built part, and we have achieved the accuracy at a very high level using such approach. What it offers is whenever we are doing 3D printing, 3D printing is quite costly as the material cost is quite high. So what we need to do is also if we are basically working on any mold based modeling, so creation of initial mold is very costly. So we need to work on certain principle in which we can reduce out the cost. So the industrial accuracy could be increased and we have the less dependency and the less wastage of material to be come as output. So what we do is we have designed a particular part, we have done the 3D printing. Now the part is again being scanned. Why so? Because we need to check how the changes are occurring with the design part as the particular output that is being generated. Once it is done, we move on to the next part. So we identified the different region that were corresponding to the weak point. It is aluminum, silicon, magnesium material, composite-based material through which the printing was done. It was a metal additive uh, uh, printing for a heat exchanger model that was created in which coolant would be in from one point and the particular output was will be taken from the outlet unit. The scanning was done, it was computed. Later on, a particular surface deviation tool was also being used to check out for the surface deviation accuracy, whether the particular parts are being highlighted out or not. And in the surface division tool, the result also came out to be very good. We checked the accuracy was pretty high. Later on, you can see there are some internal lattices that were generated to develop this material. So this was inspected and some of the lattices were having weak points. So for example, this particular region was having weak point and the particular lattice was getting covered. So what we had done for such case was we had done the improvement. We have told the particular parts to be redesigned for the areas to be met for, and the particular mesh included all the regions. So when once it is a city, so we can identify the different regions that are being present in the data set. So the part was identified as metal part, of which the particular 3D printing was done. The fluid that is being the coolant that was being inserted in the heat exchanger, and then the air part that will be injected to. So this way it was done. Once it was done, a CFD model was again generated. Once the remeshing was done, surface deviation was calculated, and the part was later on exported out to console software for doing multi-physics analysis. Once the result was produced, the conclusion came out to be great. And it is one such example that can be taken for any part. So even if we are developing any engine part, or even if we need to check the fittings, we need to check the sizes, how the defects are occurring, what are the weakness point. We can check that easily without any destruction of any part. For example, if this point is corresponding to weakness, we can just do a finite element analysis of the same. And once the result will be with us, we can easily identify the points, we can do the corrective measures, and ultimately produce out the uh, better output and better result. Now, the case study 2 involves the analysis of additively manufacturing coronary stents. Stents play a huge role. As we can see, there are huge number of cases related to uh, heart attack that patients face. It is generally with the blockage of any artery. To correct that out, what a surgeon usually performs is he places out a stent to clear out the blockage, and the stent is first of a very minimal size. Once it is inserted inside the particular artery, it is again expanded to free up any clogging that is present, any blockage that is present. So, why this particular approach is used? Why we are doing an FA modeling? It's very important to understand because the particular strength models that we currently have in market or are being generally used from past 30, 40 years. It is designed for everyone, it is designed the same. There is no changes. Now, what the industry is being shifting is to develop the patient specific strength. So there is a reduction in the loss, there is a reduction in the casualties while operation is being performed. So to do that, we need to have the most accurate stands. So once we are doing the 3D printing, we aren't that sure whether the particular printed part would rely for a significant amount of time. So we need to do an analysis of the same. We need to do the bench testing of the particular product, whether it will take any wear and tear over a period of time. And every product does wear and tear over a period of time, but we need to take the time into consideration because if a wear and tear is occurring after 20, 30 years, then it's of no issue because that's the specific lifespan for any implant parts that is being inserted. So coming back to the point. So what was done is a particular stent was done. So stent model was designed in a CAD software. It was done. The 3D printing was done. Additive manufacturing was done. Then LPBF stent was again taken. It was put in simple way. It was aligned with any coronary artery. Then it was a particular mechanism was shown when we have inserted and when we have floated the particular part, how it was done, how the particular changes occur. And the result came out to be when we are doing the epiponding, there were some big points that were there. So let me move a slide back. There were some big points that were present in the stent model. So the corresponding blue regions that you are seeing are the basically bed points that are present. So the particular surface was redefined, then it was remeshed, then we have a proper structure, and we can see how accurate the wall thickness came out to be. And it is a uniform wall thickness that came out to be after the particular FA modeling was done, then FA finite element analysis was conducted. The mechanical properties were set for the specific strengths by combining the testing and numerical analysis of different stent models. So three different models were taken. So one was only heat treated, one was electropolished and heat treated, and another one was the CAD model that was taken. So you can check the particular node points why the particular finite element modeling was created out. So this one being the heat treated model, this one was a heat treated followed by electropolished stent model, and this one was the CAD model that we have designed. So we can see how smoother of a mesh is generated in this particular CAD model. And when we are doing the heat treatment and electropolishing, the mesh is still smooth. But when we are only doing the heat treatment of the particular part, so there is a lot of roughness along the surface, along the particular node points that is being present, which can cause a fracture over the part, and it will cause high stress in the part. And we need to reduce the stress and strain in any part that we are working to for the efficiency to be of a higher value. So this particular analysis was done, and later on the result came out to be the particular CAD generated model was the best efficient model. It was exported to Similia Abacus FEA software for doing the structural mechanics analysis, and the result came out to be very good. We can see the force versus displacement of the different models that were reconstructed. So it was the LPBF model in which the heat treatment was done. So we can see.
that there is a lot of force versus displacement over here. This was the intended LPV of the stand, the CAD model, and we can see the uniformity around the particular intended LBPF model. And later on, we have the heat treatment followed by electropolish. So this way, any part can be studied out. We can combine computational fluid dynamics study with the finite element analysis, and we can reduce out the most accurate part. Now, taking up the third case set, it is an intensity that is taken. It is one such example data set that is also present in the software. So when any user wants to use such example, he can use in a very easy way. What we need to do is we just need to load the intensity data set. It was generally done to check the placing and fittings inside the particular engine city, and once the placing and fittings were placed, the particular model was generated, a finite element model was generated, and again the finite element analysis was conducted. So how the particular process got through, we have taken the engine city in simple way. You can see the placeholder and fittings over here. So we have the placeholder corresponding to which the fittings was done. This is the engine city in the 3D view. The segmentation was conducted. It was an easy, quite easy segmentation because there is a clear identification between the grayscale regions from the vacuum corresponding to the particular nearby region. So it was a pretty easy segmentation. The resolution over which the scanning was done was a 0.4 mm plus 0.4 mm plus 0.5 mm. So it is a very high end resolution. Why we require such for engine part or any automotive part to get the highest of accuracy, because the lesser the number over here, the higher would be the output, the higher would be the number of slices, and we can see the layer by layer differentiation of different parts that are present. So we have done the initial visualization. In the visualization itself, certain defects were easily seen, but once we had done the segmentation, we can have a better approach because the fittings were calculated according to the placeholder uh, space, and once the particular fittings was done, we have set out the walls. So these are the balls and fittings that were conducted, that were generated over here. Once this was done, we have done the multi-part segmentation followed by the fitting, and the ultimately particular finite element model was done using the plus FE module, and later on the result was again exported to LS software for doing the preliminary analysis of the impact caused by the presence of any void. So whenever there are voids present in the data set, there might be a loss of some efficiency. So the point at which the loss was occurring, the points was corrected to make sure the particular intake and exhaust temperature came into the constraint value. And once this was done, a proper defect analysis was done for the same. Now we are getting on to the last case study in which an head model was constructed. I had taken this case study for one simple reason. It tells us how biomechanics plays a crucial role in the understanding the human anatomy. So what is done in this particular case study is an in vivo MRI scan is taken of a 26-year-old male, and you can see in the MRI we can have the proper structural visualization, the soft tissue visualization, but still the hard tissue visualization is not that proper. But we were able to complete out the segmentation. The segmentation had total of 12 different structures, and whenever the particular structures were taken for, so for example, the particular cranium was taken as a different structure, the cavity brain cavity was taken as a different structure, sternum was taken as a different structure, then the spinal region, the spinal cord connection with the brain was taken, then all the hypothalamus वगैरह again were considered, they were still segmented out. All the smaller tissues, all the parts that were carried out to have a proper study generated, that was taken into consideration. We have done the multi-part FE measure. So this is a proper view of the same, because in this particular it is not that proper, but in this view you can see how we have done the cranial cavity segmentation. It was the spine, the spinal cord, and the particular trachea. So once this particular study was done, we had done a final meshing for the spinal cord and the spine and the head region.
Why? Because we needed to know how, whenever there is accident, how impact would it take, at what point the risk is of the operating cost for us. So what we did was we had taken a head model that was specifically designed for this particular MRI patient that was taken, and we have placed out this particular helmet over this patient. Once it was done, again a whole remeshing was done for the outer surface, the skin region, as well as the particular helmet that was taken. The helmet was interactively positioned with the image data set that we were working on. Once this positioning was completed, we have done the remeshing. The next part came out to be what are the points of impact whenever an accident occurs. So blasting was done for this particular case, and once the particular blasting was done around different angles, we came out to be this is the most important region that needs to be covered, and this being these two being the most important regions that need to be covered while developing out a helmet. So this was a case study done for the American football, that is rugby, that is being played. So, but it is all it was also later adopted by US Navy to do the same for military helmet generation. So this can be done in a similar way. Such studies can be conducted in India too. If any of the particular participants that are interested in conducting this research studies, this can play a crucial role because redefining safety while we are driving is one such important component that is not that catered but needs to be understand why it is of the topmost priority and topmost important for us. So this way, to do any sort of analysis, it is very easy. We can directly import any scale of that file, bring it in, position it with image data, and later on carry out the results for that. So this is the overview of the case studies and the image basics of image segmentation. In the afternoon session, I shall be covering out the particular same part, how to do the multi-part segmentation. I will take an example of rock microcity that I have from one of our clients, in which I'll show how different parts are identified for a multi-part segmentation. And we shall also be covering out the finite element model. We will be also seeing the 3D printing and the measurement section. So the session is open for question and answer. If anyone has any questions, they can let me know. Hi. So any questions? Yeah. Thank you. Thank you, Dr. Sharma. No issues. If there are any questions from this session and needs to be covered in the next session.
Ayush,
Yes, sir.
I just wanted to means last time I shared my details as I'm not able to register
Yeah.
for
I,
the software.
yes, yes. I have already raised the issue, sir, to the team. They are working in the background for the same. I'll update you with the same once I get.
Okay, okay, okay. Thank you, thank you.
Yeah. So, any more questions? Anyone? I think there are no more questions. So, I think I can end this session for now. And we will be connecting in the afternoon session. Everyone can be join the session. And we shall be seeing the live demonstration of the cases that are discussed in this morning session. Yeah. Thanks again, everyone, for joining. Have a good day.